We're going to continue looking at improper integrals, but now we're going to look at type 2 improper integrals, and those are these integrals with infinite range. Let's look at the integral from 0 to 1 of 1 over square root of x dx. On first glance, we may think of expressing that as x to the negative 1/2 and using the power rule in reverse, but we got to be careful because let's go ahead and look at the graph of this. This is an unbounded integrand because as we approach 0, the function value is approaching infinity. So how are we going to do this? We are going to choose a value between a and b, in this case between 0 and 1, and we will call it c, and then we will let it approach 0 from the right hand side. So we're going to have the limit as c approaches 0 from the right hand side of the integral from c to 1 of this 1 over square root of x dx. Now we can express this as an x to the negative 1/2 and think of the power rule in reverse. And so we will have the limit as c approaches 0 from the right hand side of x to the 1 higher power, which would have been a 1/2, and then we would need the reciprocal of that power out in front, so a 2, and that will be evaluated from c to 1. So this is the limit as c approaches 0 from the right hand side of 2, and then here we have 1 to the 1/2, so that's just going to be 1 minus, and this would be square root of c because that's c to the 1/2. Now as we let c approach 0 from the right hand side, we can see this is going to go to 0, and so we get our value, which is 2. Now we can go ahead and summarize this in general then. If we have f of x and it's continuous on the open interval at a here, closed at b, it's discontinuous at a, such as we had here at 0, then this integral from a to b of f of x dx is going to be the limit as c approaches a from the right hand side of the integral from c to b f of x dx. Let's go and look at our other cases. If we have a function that is continuous on an interval that is closed at a, open at b, and it's discontinuous at b, then the integral from a to b f of x dx is going to be, we're going to choose a c and then let c approach b from the left hand side. We will have the limit c approaches b from the left hand side of a to c f of x dx. And then our last case, we could have a discontinuity in between a and b. So if it was continuous from a to c combined with c to b and the discontinuity is at c, then the integral from a to b, we're trying to integrate across this discontinuity, and we can split this up and go from a to c, and then we could go from c to b by our properties of integrals, and then we would, this one and this one would be working the integrals as we learned in parts a and b. So let's look at an example. We're going to evaluate from 0 to 3 1 over x minus 1 dx. At first glance we may look at this and say, oh, I know the antiderivative 1 over x minus 1, that's the natural log of the absolute value of x minus 1. But we've got to be very careful because as we look at this, if we were integrating from 0 to 3, we're trying to integrate over a point of infinite discontinuity. We have an infinite range here at 1. So we've got to be careful. We're going to have to split this up and integrate from 0 to 1 and then from 1 to 3. And because of our point of infinite discontinuity there, we are going to need to replace this with c and then let c approach 1 from either side. So we're going to have the limit as c approaches 1 from the left hand side, integrating from 0 to c. That'll take care of this piece, and then we are going to integrate from c to 3 and let c approach 1 from this right hand side. So as we do this, we can go ahead and use the antiderivative here then, and so it's the natural log of the absolute value of x minus 1. We need to evaluate from 0 to c and then add to that same thing, evaluating from c to 3, and then let c approach 1 from either side. So as we substitute in the limits and we have a look here, This particular piece right here is just the natural log of 1, since we have that absolute value, and so that is 0, so that's gone. But looking here, we need to let c approach 1 from the left-hand side, and so if we think of the graph of natural log, so we're looking here, the natural log graph looks like this, and so as we let c approach 1, this will be approaching 0, and so we see that we will be going towards negative infinity. And because of that, we don't even need to work this other piece because this is going to be unbounded. And so therefore this integral diverges. Very important then. From now on, when we see this definite integral from a to b of f of x dx, we've got to consider what the function is doing on this interval, because maybe it's just an ordinary definite integral like we're used to, but it could be an improper integral if we have an infinite range on this interval.